Hello everyone, welcome to my channel. Today we will learn about the vector database and vector embeddings. We will start by exploring the basic concepts of vector embeddings and vector database. After that, we will do a hands-on demo as usual. We will develop a small project using the PGVector extension of Postgres and Spring AI framework. So why do we even need vector database? Let's think about a practical use case. Suppose we have some beautiful pictures and we want to compare those pictures. Which of those pictures look similar? There are total 4 pictures here. First of all, how our brain compare those pictures. Our brain will try to find different characteristics or features of those pictures and try to understand the semantic context of them. Based on those characteristics and context, we'll do the comparison. Now let's get back to computer system. Suppose we want to store those digital images. Ideally, we should store in cloud storage like Amazon S3, but for simplicity, let's think that we'll use a relational database. The database table will look something like this. There can be one column for storing the binary data of the image. There can be some columns for storing the metadata like file type, file size, creation date, etc. And there can be another column for an array of tags, like for storing the tags sky, building, canal, etc. This will give us a basic way of searching the images and comparing those images, but the scope here will be very limited. We cannot make that many variations. The semantic context is missing here, which is the most important thing. If you want to search by complex feature like golden sky with congested billings, the relational database will not be sufficient here. Instead, we need a vector database. In fact, for any kind of unstructured data like image, audio, video, or even large text, the relational database will not be suitable. Vector database should be used. In vector database, one image will be converted into vector embeddings. Now question is, what is vector embeddings? Vector embeddings is just an array of floating point numbers. Here, each number quantifies a particular feature or characteristics. Let's try to understand with a very simplified example. We have seen 4 pictures. Let's think about some features of those pictures. Looking at the pictures, 2 pictures have golden sky. So one feature can be golden sky. 2 pictures have blue sky. So we can consider another feature as blue sky. Congested billings are there in 2 pictures. So we can consider another feature as congested billings. And there are canals in 2 pictures. So another feature can be waterway. Let's try to quantify those features. We have considered 4 features. For all of the pictures, let's assign some arbitrary floating point number to quantify each feature. This will make the vector embeddings of those pictures. So for picture 1, we have assigned point 1 as the value of blue sky, point 8 as the value of golden sky, point 7 as the value of congested billings, and 0 as the value of waterway, since this picture does not contain any water. So the embedding of picture 1 has become like 0.1, 0.8, 0.7, 0, like this. We have also got the embedding of picture 2, picture 3, picture 4. So the size of the array is considered as the dimension of the embeddings. So far we have used 4 features, so we can consider the number of dimension is 4. If we compare per dimension, it gives us the impression that picture 1 and picture 4 are similar. So if we compare the first dimension, the values are 0.1 here, it matches. For dimension 2, the values are 0.8 and 0.7, closely matches. Third dimension, 0.7, 0.8, closely matches. Fourth dimension, 0, matches. So we can say that picture 1 and picture 4 are similar. And picture 2 and 3 are similar in the same way. So the dimension wise values closely matches. Here we have used our intuition to understand the similarity of vector embeddings. The actual similarity or dissimilarity among vector embeddings is calculated using some mathematical model or formula. We'll come to that point later. Now, if we pick only two dimensions from each of the embeddings and plot those in two-dimensional graph, it will look like this. In x-axis, we have plotted the golden sky feature, and in y-axis, we have plotted the congested buildings feature. So the graph has become a vector space now. In this vector space, similar items are positioned closer, dissimilar items are positioned far apart. So two clusters have been created here. In one cluster, picture 1 and 4 are placed. In another cluster, picture 2 and 3 are placed. This is a simplified two-dimensional graph. For real vector embeddings, there will be hundreds or even thousands of dimensions. We also need to find the relative similarity or proximity among the vector embeddings. To do this, we need to use some kind of mathematical model. This is called the vector similarity metric. There are many ways of doing it. Let's discuss a few of them. The first one is Euclidean distance or L2 distance. This is the straight line distance between two vectors. We first calculate the squares of the differences between the vectors' corresponding component. Then we take the summation of square values. Finally, the square root of summation is taken as the Euclidean distance. For example, vector A has dimension or component as A1, A2 up to An. Vector B has dimension or component as B1, B2 up to Bn. The formula will look like A1 minus B1 square, then A2 minus B2 square, An minus Bn square. We'll take the summation of all the squares, and finally we'll take the square root of the summation. The next one is dot product similarity. This is calculated by taking the summation of products of the vectors corresponding component. So for vector A and B, we are taking the products of A1 dot B1, then A2 dot B2 up to An dot Bn. Then we will take the summation of all the products. The next one is Manhattan distance or L1 distance. This is calculated by taking the summation of absolute differences of the vectors corresponding component. So the formula is for L1 distance of vector A and B, we are taking the summation of the absolute differences of AI and BI. The last one we'll discuss is cosine similarity. This is the measure of the angle between two vectors. We first calculate the dot product of the vectors. The formula of dot products is already discussed. The dot product is then divided by the product of the magnitudes of the vectors. So how we calculate the magnitude? The magnitude is calculated by taking the square root of the sum of squares of the components of the vectors. So for vector A and B, first we take the dot product and then it is divided by the magnitudes. So how we calculate magnitude? We take the square of each of the components and then take the summation of the squares and then finally take the square root of summation. So the value of cosine similarity ranges from -1 to +1. Here -1 will represent it is fully opposite, +1 will represent identical vector, and 0 will represent orthogonal or unrelated vector. Example use case of cosine similarity is it can be useful for semantic search or document classification problem because it allows us to compare the directions of the vectors. We have discussed many points about vector embeddings so far. Now the question is, how are the vector embeddings even created? Basically, we need to use some kind of embedding model to do it. Embedding models are, in essence, the machine learning models. These have been trained using massive data sets. So we have unstructured data. Those are passed in embedding model, and then we get vector embeddings. So we have many kind of unstructured data like image, audio, video, and even large text. So we have vector embedding models for each type. Like for image data, we can use clip. For audio data, we can use WAV to vec. For video data, we can use video BART. For text data, we can use Glove, GPT, BART, etc. Until now, we have learned how to generate vector embeddings. The next step would be to store those embeddings in some database. We need to use any vector database for this purpose. There are many popular vector databases available now, like Chroma, Pinecone, Weaviate, Milvus, Redis. Redis is popular for caching solutions, but it can be also used as vector database. And finally, Postgres database with PGVector extension. We'll show a demo of vector embeddings using PGVector. We know Postgres is a very popular relational database. This is widely used for enterprise projects. PGVector is an open source vector similarity search extension for Postgres. With the PGVector extension, we can use all the benefits of relational database like ACID properties and so on. At the same time, it will work as vector database. We can install PGVector in two ways. One way is to install it in local Postgres server. Another way is to use Docker image. I will show the Docker image part later. Let's try to install in local Postgres first. I will show the installation steps for macOS. From terminal, let's enter into temp directory. So we need to clone the repo of PGVector like this. So the PGVector repo has been cloned. Now we need to enter into PGVector directory. Now we need to export the path of pgconfig from Postgres installation directory. And finally, we'll use the make install command to install PGVector. So PGVector has been installed in our machine. Now we need to enable the extension. I use the dbeaver application to export the database. We need to execute one query to enable the extension. So there is already one database here. In this database, I will enable PGVector extension. But PGVector extension was already installed, so I get this response. So now we will create one table, and this table will contain one vector embedding column. So this one is the table, and it has one vector embedding column with dimension size 3. Now we can insert few rows in the table. So let me insert 2 rows with vector embedding. So 2 rows have been inserted with vector embedding column. We can try to execute a vector similarity search query now. So here is an example query for getting rows within a certain distance. And here we have used L2 distance. So this one indicates L2 distance. PGVector supports operator for many vector similarity metrics. Uh, Here are the supported distance operators or functions, and we'll use cosine distance operator later. Now let's remove the items table. This will be required for our next example. So far, PGVector has been installed and working fine in our machine. Now let's develop a project with Spring AI and integrate PGVector there. In fact, I have already developed a project and pushed it to GitHub. Please clone this repo from here before watching the rest of the video. This will help you to understand better. Let me explain the project now. As usual, we'll start with pom.xml file. This is a Spring Boot project. The Spring Boot version is 3.5.5. The Java version is 21. And we have used a Spring Milestones repo this time. And we'll need the Spring Boot Starter Web because we'll develop a REST endpoint. And we will need this Spring AI OpenAPI Spring Boot Starter because we'll use OpenAPI model and API. For database part, we need to add the dependency Spring Boot Starter JDBC and Postgres SQL. And for DB migration, we have used Flyway. Let's explore the application.yml file now. It contains the data source configuration, URL, username, password. It's pretty standard. It then contains the configuration for OpenAPI. We need to provide an API key. If you don't have any API key, please create one from the OpenAPI platform. One point to note, you need to add some balance in your OpenAPI account. The amount can be very small. Without any balance, the API key will not work. The rest of the configuration is about the chat model and the embedding model, and then server port. This is pretty standard. And finally, we have created one custom configuration to enable or disable the embedding generation step. Now let's move to DB migration. We have used Flyway library for DB migration. There are 3 migration scripts. In the first script, we have created the extension, and then we have created one table which contains quotation from famous person. There is one column for storing the quotation. The next column is about the person's name who made the quotation. And last but not the least, we have one special column for vector embedding. The size of the vector embedding column is declared as 1536. This part is important. It should match with the dimension size of the embedding model text embedding at a 002. So basically, the dimension size of these embedding models is also 1536. In the second script, we have used some DML queries. There are some insert queries to populate the quotes table with some quotation values. In the third script, we have created one index on the vector embedding column. I will cover this part later in detail. At this stage, if we run the application from main class, then the DB migration script will be executed and the quotes table will be created with some rows. I am using IntelliJ and I have created one run configuration to execute the application. Here we can provide the necessary environment variables like this. Let's run the application in debug mode. And from the log,
we can understand the DB migration has been executed. From dbeaver application, we can see the course table has been created and 10 rows have been inserted. Each row contains one quotation. The quote column and person column have been populated. The values of the embedding column is null. We'll calculate the vector embedding for each of the rows, for each of the quotation values, and update the embedding column. We'll do this by using our project code. We have created a code generation class. It implements the command line runner interface. We inject one instance of embedding model, one instance of JDBC client. The embedding model class will be used to generate the embedding, vector embeddings, and we'll do some database operations. So we'll need the JDBC client, and the method is generate, and here is the query for getting all the codes from the course table. So basically we fetched all the rows from course table, then extracted the value of quote and person, then we concatenated the values of person and quote to generate the input for text embedding, and then we have generated one embedding request. It will take the text input and then create a embedding request. So from the embedding model instance, we'll call the call method and we'll get an embedding model response. This embedding response will return as a float array, and this contains the vector embedding. So we need to convert the float array to a list of double. So this will be the text embeddings. And now we need to update the embedding column using the update query. We will not execute this query generator class every time we'll run the application. Thus, we have created one configuration to enable or disable the embedding generation step. So currently the value is true, so the embedding generation step will be skipped. Let's set the value to false and then run the application again. From the log, we can see the embeddings are being generated now. Let's check the database table now. So the embeddings are updated in the table also. Cool. As the embeddings are generated now, we can try some semantic search of the quotation values. We will take a search query or prompt from the user. We'll calculate embeddings of the search prompt. Then we will do a similarity search using the cosine distance formula. Let's see how we can implement in the code. We have developed one code service class. One instance of embedding model has been injected. One JDBC instance has been also created. We have declared one method, search codes. It takes one string parameter prompt. So using the prompt, we create one embedding request, and using the embedding request, we execute the call method of embedding model. It gives us the embedding response, and this embedding response eventually becomes the prompt embedding. So using the prompt embedding, we'll do the similarity search. So we'll apply the cosine distance formula to perform the similarity search. The formula is like 1 minus cosine similarity. The whole query is like this. and we have used the cosine distance operator, and we have also used one threshold value. The threshold value is 0.7, and the interpretation of the cosine distance is also mentioned in the comment. Here, the value near to 0 means vectors are identical. Value near to 1 means vectors are unrelated or orthogonal. And value near to 2 means vectors are completely dissimilar. After the query is executed, we'll get a search result as a list of code objects. And finally, we have exposed this method in a REST API, and we have created one code controller class and implemented one get/codes endpoint. It takes the prompt as a query parameter and then call this search code method. Now let's run the application again and call the get_codes endpoint from Postman. Let's first search by prompt book. So we have got 2 codes related to books. Now let's try to make the code a little bit bigger, like codes of book. So we have got the similar result. We can also make it as codes of publication. It has also returned some result related to books. We can change it to codes of love, for example. We have get 2 quotations, related quotations. Now if we use a synonym like affection, this is also return the result. So here the prompt has been converted to vector embeddings internally. So it acted as the contextual meaning here. So this has become an example of semantic search. We can use the PGVector extension from Docker image also. Let's see how to do it. There is one Docker file and one Docker Compose file in the project. The Docker file is similar to any standard Spring Boot project. In the Docker Compose file, there are 2 services. One is Spring Dockerized app and one DB service. The DB service contains the image of a Postgres server, and in this image, the PGVector instruction is pre-installed. So this part is important. And as environment variable, we have provided the DB credential. In the Spring Dockerized app service, it depends on the DB service. And as environment variable, we have provided the DB credential, and also the open API key needs to be provided. And to provide those environment variable, we have created a separate environment file, .env file, and we need to provide the API key here. Let me provide my open API key value and run the docker compose up command. So the service has been started and the DB migration is also completed. Let me check whether the database have been created properly or not. So I have created a separate connection for Docker DB. Okay, the table has been created and 10 rows have been also inserted with the quotation values. The embedding has not yet been generated. We need to generate it again.
Now let's generate the embedding in the same way we did earlier. Let's stop it now. And from the Docker compose file, we can use this environment variable and then run it again. From the log, we can see that the embeddings are now being generated. Let me check the database table. So the embeddings are generated in the database table also. The semantic search via REST API call will be similar. Using Postman, let's call the get codes endpoint again. Yeah, it's working. The database table we used for this demo contains only 10 rows. How about when there are millions of rows with vector embeddings and we need to perform a similarity search? We also need to remember that each embedding has thousands of dimensions. The regular similarity search will become very slow in such cases. To make it faster, we need to use a process called vector indexing. Vector indexing uses an approach called approximate nearest neighbor or ANN. The idea behind ANN is to pre-calculate the distance between the vector embeddings and then organize and store similar vectors close to each other, either via cluster or graph. This helps to find the similar objects faster. With ANN approach, there can be little trade-off though. We may lose a little bit accuracy to gain the significant speed improvement. There are many vector indexing algorithms. Most notables are HNSW or hierarchical navigable small world. This is a graph-based method. It connects vectors to their nearest neighbors and it creates a multi-layer graph. The next one is IVF or inverted file index. This algorithm partitions the vector space into clusters and then searches only within the relevant clusters. For our demo, we have applied HNSW algorithm. As the final point, let's discuss some applications of vector database. Vector database can be used as the long-term memory for LLMs. Then vector database can be used as semantic search. We can search based on the meaning or context, not with the exact string match. In our demo, we have seen an example of semantic search. Then we can do similarity search. We can find files with similar image or audio or video data. Then recommendation system. So with recommendation system, it can suggest items based on previous purchases of the customer. And finally, RAG, retrieval augmented generation. Vector database is a core feature for RAG. And this will be the topic of our next video. So stay tuned. Hope you have enjoyed this video. See you in the next tutorial. Thank you.